Assalamu alaikum. I am MD Emon Hossain and this subject is Aircraft Design 1 and my group name is Kaizen. So let's begin with the presentation. So in this subject we are given 4 projects. Project 1 was about feasibility study, project 2 about aircraft aerodynamic study, and project 3 about aircraft performance and aircraft stability, static stability, and project 4 was about design landing gear of the aircraft. So for me, I will talk about the feasibility study, which is project 1, and design mini UAV with fixed wing detail. So we have divided 4 projects into 4 members. So I'll talk about the project 1 and my other members will talk about other 3 projects. So we have chosen 25 unnamed aerial vehicles and included their type and mission. So UAV types was mini UAV fixed wing with detail 5 to 50 kg. So here are some models that we have find out, and I have included only 3 aircraft here, but we have got 25. Even it was difficult for us to get collection the data about the UAV because it's too conventional. So but at last we have find out 25 aircraft, and here is the model Jump 20 UAV, CGT45, SLT UAV, and work MQP. And here the data collections. In data collection part we have made some tables and put the data, like here I have put 3 aircraft name, 3 UAV name, and type of their engine, and then the power of the engines, and then weight estimation here, and wing of fuselage area. So these are the data collection part. We have successfully did also data collection about UAV. Then we have plotted the graph by referring to RIMET 2006 edition book. Here it's, we have got so many graphs, but here are some pictures that this kind of graphs we have got from the values. And then for our UAV we have made this sketch. So this was our initial sketch of our UAV. And then aircraft profile. So the following are the list of the design aircraft specification and configuration. So we have give our name of the aircraft is Kaizen M8. So assume gross weight 47 kg. Type was unmanned aerial vehicle. Regulation unmanned security drone, and accommodation 0 on board and 1 in ground station will control the aircraft. And mission was fixed wing detail UV 5 to 50 kg. Then this specification estimation of the aircraft. In this part we have done the things correctly. And wing specification, we have choose the fixed wing hybrid VTOL, and tail specification detail, and power plant 2-cylinder gasoline and multi-fuel UAV engines. And for external dimensions, areas, weights and loadings and performance, these things we have also calculated nicely. And then we have isometric and orthographic drawing of the UAV by using SolidWorks. Actually this is the final drawing of our aircraft, and we can see that how is the front view, top view, front view and side view. So here's the design of the new model. And then weight estimation. So takeoff weight structure we have given the crew weight was 0 as there is no crew, and payload weight WP equal to 4 kg. And mission profile, here is the simple cruise mission profile: takeoff, climb, cruise, descent, loiter and land. And then weight of components. So in our aircraft, wing weight estimation we have got 10 pounds is equal to 4.65 kg. Fuselage weight estimation, horizontal tail weight estimation, vertical tail estimation, fuel system weight estimation, engine weight estimation, electrical system weight estimation, flight control and weight estimation. So here are the values we have got after the calculation, and overall it was less than 55 kg. So center of gravity estimate. So the following formulas allow the calculation of the center of gravity for each of the 3 axes. So here are the formulas that we use to calculate the center of gravity of empty weight: maximum center of gravity, forward center of gravity, and backward center of gravity. And center of gravity of various components and center of gravity different condition we have also get. Here is the model, and there's the picture. You can see that here weight and balance of CG of various various components here, and this is the weight and balance CG of different conditions, the center of gravity. So we have also shown these things successfully. And then after all, final conclusion. So to sum up, in this project, a feasibility study analysis is an important part of the engineering design, and particularly in aircraft design. So the mini UAV fixed wing with detail 5 to 50 kg is the identify the need in this case for our project. So we researched and put into practice what we learned about feasibility studies from other UAV drones, and then such as discovering aircraft parameters, configuring aircraft parts, estimating aircraft specification, and estimating weight. As a result of this, we investigated and conducted research before creating our own design. So after the feasibility study is completed, we can move on the aerodynamic analysis of our aircraft, which will be our next project. Thank you.
Assalamualaikum and a very good evening. My name is Muhammad from Group 1, and today I will talk about our project 2 for aircraft aerodynamics. So my presentation outline will cover up to chapter 6. Firstly, I will talk about our chapter 2, which is the aircraft configuration. So in project 1, we have calculated various UAV parameters estimation which is in an acceptable range, and then by using the formula in project 2, we are able to calculate the maximum lift coefficient of 1.53 and array numbers of 0.9 times 10 to the power of 6. So for the section lift, there are two parts, which is the section 0 lift angle of attack and section lift curve slope. For the section 0 lift angle of attack, we obtain the following parameters. This is because we refer to graph of maximum lift coefficient versus ideal lift coefficient for several NACA airfoil sections. Then we obtain that the wing airfoil ideal lift coefficient is 1.789 and the wing airfoil net maximum lift coefficient is 1.944. since there are no subtraction of value from high lift device contribution. Next is the section lift curve slope. To determine the lift coefficient angle of attack according to the method for the development of the boundary layer for airfoils with transition fixed at the leading edge and with maximum thickness less than approximately 20%. The airfoil section lift curve slope at Mach numbers up to critical Mach number is given by the following equation. And then by using the deck method, we obtain these parameters by referring to lift curve slope graph. And then we insert these parameters into the project 2 equations. We are able to obtain the lift coefficient angle of attack in theory, which is 6.89, in test 0.0982 per degree, and the angle of attack at 0 angle is 0.7399 degree. Next chapter is the wing alone configuration. In aerodynamic characteristics, both of the wing lift and wing drag are important parameters. Based on the calculation done in chapter 3 of our project report, we have calculated the value of zero lift drag is 4.29 times 10 to the power of negative 3. From the value of zero lift drag, we have calculated the lift coefficient and drag coefficient at different angles of attack as shown in a table in our project report. Therefore, the graph of the lift coefficient versus angle of attack and graph of drag coefficient versus angle of attack is shown in figure 1 and figure 2. Next is the body alone configuration. By using the DECOM method from the DECOM handbook, the aerodynamic coefficients were obtained from the lift curve slope of the body alone, where the skin coefficient friction is 0.0051. Then the lift coefficient and drag coefficient changes when the angle of attack increase. These changes can be seen in figure 3 and figure 4. So that we can observe that the thread line coefficient of the graph is linear and greater as the angle of attack increase, where the lift coefficient has a higher value than the drag coefficient. Following chapter is the wing body configuration. So we know that by using DECOM, we can discover the wing body lift band incline, which is 5.6268 per radian. The wing body lift band incline is being determined concerning the Kn, Kw, Kb, where the addendums address proportions of the nose lift and wing lift within the side of the body and the body lift within the side of the wing individually. So by having wing body lift band incline, we then at the point can find the lift coefficient of the wing body at no approach. At last, the condition of wing body lift coefficient can be acquired. For the lift coefficient, the worth differs as it is straightforwardly relative when contrasted with the approach alpha. For wing body, alpha is the new variable approach relative with the fuselage baseline. Then at the point later we get the wing body lift band incline, we continue to find the wing body lift in the nonlinear approach range, because in the graph we can see that figure 5 we plot the wing body lift coefficient versus angle of attack. This shows a linear relationship when in a linear approach range. For a non-linear approach range, we can see in figure 6 where see the lift coefficient and alpha in the straight approach range. We can consider that lift alpha differs to the approach increments. Finally, for wing body lift, we compute for wing body greatest lift. For this segment, we really want to compute the wing body most extreme lift in two conditions. The first condition is the greatest wing body lift, and the second is the approach of the coefficient of most extreme wing body lift. Next is the wing body tail configuration. So the method 1 is chose as the span of the forward of the UAV surface is large compared to the after surface. As per this method, the lift coefficient of angle of attack obtained is 6.311 rad. This is followed by the calculation of wing body tail maximum lift. For this calculation, the following equation is used. So the wing body maximum lift is assumed to be the same as wing body angle of attack at maximum lift. The tail lift is in the above equation is the horizontal lift in the presence of wing body and vertical tail based on the wing area. Hence, the lift values obtained is 2.29. So we can see that the CL alpha versus angle of attack is plotted. In conclusion, the wing alone is important because we compute the aerodynamic force acting on the wing alone in order to get the wing lift, wing drag, and wing pitch moment. The body alone configuration is important because when computing the body alone, in which we must determine the lift and drag coefficient as well as the pitch moment, all formulas and graphs are taken directly from the DECOM manual. The wing body configuration, the same holds true for the wing body component, for which we must compute lift, drag, pitching, lift, drag, and pitching moment. So lastly, the wing loading, we use the Schreck's method to determine the wing loading. This is to observe the variance in wing loading at various conditions. As a conclusion, the aerodynamics qualities are critically in determining whether an aircraft is safe to fly. That's all from me. Thank you.
Assalamu alaikum. I'm Ahsan and Rifat. I'll be discussing Project 3 aircraft performance and stability. For aircraft performance, the determination of performance variables such as range, endurance, rate of climb and takeoff, and landing distance, as well as flight path optimization, are all part of aircraft performance. The aircraft weight, atmospheric conditions, runway environment, and the fundamental physics rules regulating the force acting on the airplane are all elements that affect aircraft performance. And for aircraft stability, when an aircraft is disturbed, it has the tendency to return to its original state by itself, which is known as a stability. In flight, an aircraft can rotate in 3 dimensions: yaw, pitch, and roll. For aircraft performance analysis objective, we need to determine the thrust required, power available, rate of climb, maximum velocity and maximum rate of climb, absolute and service ceilings, range and endurance, takeoff performance, landing performance, turning flight. And for aircraft stability analysis, we need to determine two moments on the airplane: longitudinal static stability, contribution of the wing to MCG, contribution of the wing body to MCG, contribution to the tail to MCG, total pitching moment about the center of gravity, equation for longitudinal static stability, neutral point static margin, lateral static stability, directional static stability, and handling qualities. Here's the aircraft configuration with the max cruise speed, stall speed, service ceiling, gross weight, empty weight, and the aircraft drawing from the SolidWorks. And for analysis of the aircraft performance, the aerodynamic drag, we get the different CD for different CL. Our maximum CL is a 1.503, and we calculate from the equation CD equals to CDE plus CL square divided by pi E aspect ratio. Thus, for thrust required, we use the velocity equals to 40 meter per second, and we get the thrust is at 33.034 newton. Here is the maximum velocity and maximum rate of climb at a sea level. We input the different velocity 50 km per hour, 100, 150, 200, 250, 300, 350, and we get all the values for CL, CD, thrust required, power available, power difference, and rate of climb for each velocity at sea level. And here is the graphs for the different sea level 1000 meter and at 4000 meter. For blue line is indicated to power required, and the orange line is indicated to power available. And the four bottom graphs are rate of climb against the velocity for different height. And the for absolute and service ceiling, we get from the graph we get the service ceiling is 6000 meter and absolute ceiling is 9500 meter. And for range and endurance, our range is 45.41 kilometer and the endurance is 38173.52 seconds. And for aircraft takeoff performance, we need to get the value of SLO. For SLO, we need to calculate the VLO, and our SLO is equals to 164.1 meter. And for landing performance, we also need to take values for SL, and for SL we need to calculate the VT, and after putting all the values in the equation, we get the value for SL equals to 103.446 meter. And for turning flight, our omega is 0.489 per radian per second. And for VN diagram, with the load factor with different point with the different G's with the different velocities. For analysis of aircraft stability, longitudinal static stability, contribution to the wing to MCG is a 0.02785, contribution to the wing body to MCG is a 1.8227, pitching moment curve slope is a 3.3701 per radian, total pitching moment of the center of gravity is 0.05765, pitching moment tail lift curve slope is a negative 2.161 radian, and zero lift total pitching moment about CG when it's empty is a CMOT is equals to 3.01, and when it's maximum weight, its CMOT is 1.8804. And for longitudinal static stability neutral point, we get the values equals to 6.5321, and the static margin is 3.377. Okay, for lateral static stability, the rolling moment for the debris due to side is slip is a CL beta, and our value is negative 0.013 per radian, which is less than 0, and we can conclude it's stable. For directional static stability, our CN beta is equals to 0.2114 per radian. It's greater than 0, so we also can conclude that our UV is stable. In conclusion, all calculation and assumption of the aircraft performance and stability were obtained using the methods suggested in the project notes and also from the reference given. The empirical method is a combination of theoretical and wind tunnel testing. All parameters are obtained from our preliminary design. In the previous project, graphs and tables are illustrated are computed by Microsoft Excel. Therefore, from our analysis of the performance and stability of UAV, we can say that we have achieved the objective of this project. Thank you.
Assalamu alaikum warahmatullah. My name is Mohannad Raihan. I am one of the group members from the group Kaizen. Today I am presenting our project 4, which is a landing gear design. So from today I follow this outline, which is introduction, literature review, methodology, analysis and result, discussion and conclusion for our project. So introduction, landing gear is an aircraft undercarriage that may be used for takeoff or landing. The system is vital subsystem of an aircraft and is often configured in combination with the aircraft structural configuration. And for landing gear design, we need to follow some parameters. So today we are following this 12 parameter, which is type, fixed of landing gear, height of landing gear, wheelbase, wheel track, the distance and angle between main gear and aircraft center of gravity, main structure and substructure sizing, tire sizing, component used, load of each structure, and strength analysis and tail drawing. So objective for our project 4 is to study the configuration of static load and tire sizing of the aircraft, aim to produce a concept design of the landing gear using SolidWorks software, to perform the finite element analysis on the design, and finally applying the stress analysis on the landing gear of the UAV Kaizen M8, which is our UAV. So before you go to proceed, so our aircraft profile is the UV specification is assume gross weight is 47 kg. Name of our aircraft is Kaizen M8 and type is unmanned aerial vehicle. Regulation which will be used as a security drone, and accommodation will be 0 on board and 1 in ground station. Mission is the fixed wing T-tail UAV 5 to 50 kg. And wing specification is our fixed wing hybrid VTOL. Airfoil is NACA 0012. Aspect ratio is 4.308. Taper ratio is 0.8. And tail plane specification is our T-tail, and the airfoil select is E182 airfoil, and specification. So for the literature review, during taxi, takeoff and landing, an aircraft landing gear serve as a suspension system. It is made to absorb and disperse the kinetic energy of the landing impact. So as you can see in this figure, this is a main component of the landing gear, such as retraction, actuation, downlock, and the drag force, F brace, Ole cylinder, Ole piston, axial beam, etc. So the types of landing gear. So there's a lot of type of landing gear. So one of them is a tricycle type landing gear, consists of the main gear and the nose gear, and is the most common from the landing gear. As you can see from the figure, this is the tricycle landing gear design. And for our methodology part, so we are following this flow chart for our landing gear design. As you can see, the first we have to identify and prioritize the landing gear design requirements. Then we have to select the landing gear configuration. After that, we have to find a fixed and or retractable landing gear design. Then we have to determine the landing gear height. Then we have to determine the distance between the main gear and the aircraft. Then we have to determine the wheelbase, wheelback. Then determine load for each gear. If everything is okay, then we have to finalize and satisfying our objective. Then we will do design, and then lastly we have to optimization. So as you can see, for the landing gear configuration, as our landing gear drone is Kaizen M8, we using tricycle type landing gear. As you can see from the bottom view, how it looks, the tricycle landing gear design. And for our wheel track, our from one wheel to another one, the distance between each 10.40 mm, and the height for landing gear is 150 millimeter, and wheelbase distance is 32.71 mm, and the angle is 10 degree. And as you can see, our new CG will change after if we put the landing gear. And this is the front element analysis. As you can see, like our modeling. So this is the SolidWorks design model for our full assembly of landing gear with the lower part of fuselage and main gear landing overview, and this is the nose landing gear overview. And for front element analysis, we have to select any material. So for our landing gear design, we are selecting the element is aluminum alloy. And for the aluminum alloy, these properties, values, and the weight of the design aircraft is 460 Newton. The weight is considered as the only loading that will extract on the real landing gear. So as you can see, the pink this is the weight of the landing gear. And generating the mesh is the last step of the modeling before starting to the analysis. So generating the mesh is one of the important aspects to be considered, because it will produce the better accuracy of the result. For the project, the mesh of the that we use is the triangular or tetrahedron faces that connect each other with the face and the node. And for the result, first we have to finalize the tire sizing. Based on the Ramsey approach, the main landing gear or rear landing gear carry out about 90% of the maximum weight during takeoff and landing. Meanwhile, the front gear landing or the nose gear landing will support the rest of it, which is about 10% of the weight during the takeoff or landing condition. So based on the Ramsey approach, the diameter for our main wheel is 127 mm, and the width for main wheel is 14.79 mm. Okay, so by using a fine limit result analysis, first we do the analysis for strength analysis. So as you can see, counterplot in a SolidWorks is based on the von Mises stress of the structure. Counterplot displays the variation of a variable across the surface of the model. The red counterplot is the most crucial stress of the element, where the blue color is the lowest stress of the element, that followed by the von Mises stress. The elements that near the connection, as you can see here, of the oval cylinder and the landing arm will experience the highest stress compared to the others. The curve area will be also exert the more stress compared to the other. And for deformation is done using SolidWorks also based on the counter plot. The maximum deformation is experienced at the top of the landing arm, while the part that attached to the lower part of the fuselage of the UAV. In conclusion, to sum up, the objective of the project, which include investigation the aircraft configuration, static load, and the tire size, were accomplished. Tire fixed landing gear type was selected for the aircraft that was being developed. The landing gear is not retractable due to space constraint at the undercarriage section. Having established the landing gear height, the distance between main gear to the aircraft center of gravity, the wheelbase and the wheel track parameter, and the static load on the each gear. And finally, the final geometry design of the landing gear was constructed using SolidWorks and subsequently analyzed using a finite method software for the loading condition experienced by the structural member of design element. Thank you and Assalamu alaikum warahmatullahi.